So, first the definitions, maybe. Okay, solution, it's a homogeneous mixture of two or more substances. So if we remember to the way beginning of the school year, we talked about this definition already. Homogeneous means that I can't see the differences in the stuff that's in it. So it's not like taking oil and water, which are going to have clear definitions of where one starts and one ends, and there's a slight interaction on the surface, but it's not actually mixing together. We, in a solution, will always have a solvent, and that is the liquid which dissolves the other substance. And it's going to be present in excess. In most solutions that we're going to be dealing with, this is water. So if we have an aqueous solution, it's dissolved in water. Water's the solvent. That's what we're going to see the most of. There are lots of other solvents out there. There's a lot of organic solvents. A lot of those can be carcinogenic, so we're not going to be dealing with those, but just so you know, most of our main solvent will be water. But oh, bored, stop being silly. Okay, so maybe all of my glitches are not worked out. Big time not worked out. Come on. Something's gotta work. Okay. So, the solute is the other part of any solution, and that's the substance that is dissolved. So in the lab that we just finished up, we had sodium carbonate. I wanted to say bicarbonate, that's a different thing. Sodium carbonate and the calcium chloride solutions. So those were our two solutions, and the solute in each of those were crystals to start with. I had crystal sodium carbonate and crystal calcium chloride that I mixed with water. And solutes can either be solids, other liquids, or gases. So the lab that we're doing tomorrow, we're using a bunch of hydrochloric acid and sodium hydroxide. That was already in solution before I diluted it to the amount that we needed. So it started at 18 molar for the hydrochloric acid. That's what they ship it to us as concentrated. It was already a liquid, and then we diluted it. Okay, solubility. The quantity of that substance that will dissolve to form a certain volume of solution in whatever solvent we're looking at. And we've got three types of solubility. We've got an unsaturated solution, where we could dissolve more solute into the solution without changing any of the temperatures or anything like that. We could have a saturated solution in which no more solute will dissolve at that temperature, and we'll actually have probably some excess solute present. Now, I had a great question last hour. The question was, well, would increasing the temperature or decreasing the temperature make things dissolve better? And it depends on what we're dealing with. If we have a solid, would more dissolve if I heated or cooled something? Heated, yep. What about a gas? Yeah, we'd want to cool it. We'd need to cool it to get more gas to dissolve into a liquid. But a solid, we'd want to heat up to get more of it added in. Have any of you ever made rock candy at home before? You have to heat up your water, add a ton of sugar, keep adding sugar and sugar and sugar until no more will dissolve, and then you let it cool, and that's when you start getting those crystals forming on whatever you put in it. So it starts going out of solution at that point. And then super saturated, this is what you're basically doing when you're making that rock candy. It's going to be temporary. The only reason we're able to add that much is because we've got it nice and hot. And it's eventually going to separate out. It needs something there and it'll start separating. Okay. Now some problems that will come in handy for you for the lab. So, concentration. You'll either see as a little c, or you'll see it as a big M. And the big M is used both to mean the word concentration as well as to represent this unit. They use M a lot for this. Big capital M either means concentration or moles of solute over liters, which is the unit for concentration. Liters of solution. Moles over liters. You may also see something like this, where we have brackets around some compound symbol. That means that we have the concentration of hydrochloric acid. So a bunch of different things to represent the same thing here. And the units get even a little more tricky. And we talked about this in gas laws a long, long time ago. We know things like 1 liter is equal to 1,000 milliliters. That's a good conversion to know if you don't. You can always use the staircase if you've learned that at some point. King Henry dances under dreary cloudy moons, and you just move the decimal point over however many times. If you don't know what that is, that's okay. Just know the 1 liter is 1,000 milliliters. We also know that 1 liter is equal to 1 decimeter cubed. So a lot of the time in these IB things, you're going to see decimeter cubed rather than liters. And a lot of the time in these IB things, it's not going to give it to you as moles over decimeters cubed, because that's harder for them in their textbooks to get written out for some reason. So you may see it as moles and then times decimeters to the -3. That means the same thing, which is the same thing as moles over liters, which is the same thing as moles times liters to the -1. Those are all equivalent. They're all exactly the same thing. So those would be good flashcards for you too. That way you know, you don't get confused when you see suddenly decimeters cubed on one thing, but liters on something else. So our first problem is probably the easiest that you'll see with these things. Oh, and it's just not going to play nice today. Bummer. I'll write it out. So, I'm not sure how much you have written in your notes.
2 moles
Thank
of
you.
sodium oxide dissolved in water to form 4.5 decimeters cubed solution.
Excellent. So we have 2 moles of the NaOH. And we want to know the concentration of it. So we want concentration, NaOH, which is going to be in moles per decimeter cubed, just based on what it's given us. I could write moles over liters too. So all I have to do for this one is take that 2 moles of NaOH, and I'm sorry, that's 2.00 moles of NaOH. Yep. Gotta remember those sig figs. Divided by the volume, it gave me 4.50 decimeters cubed of solution. When I calculate that out with 3 sig figs, I get 0.444 moles over decimeters cubed solution of NaOH. So not very concentrated. It's a pretty weak solution for us. There's not a whole lot of sodium hydroxide dissolved in this volume. Any questions so far? Okay. So now it's kind of working. There we go. We want to know for the next one how many grams of hydrogen chloride, or hydrochloric acid is another word for that, are dissolved in 3 decimeters cubed of a 6 mole over decimeter cubed solution. So a concentration here. So we want grams of HCl. But we are given, we've got 2 givens. We've got the volume, which is equal to 0.300 decimeters cubed. And we are also given the molarity of that thing at 6.00 moles decimeters to the -3rd. All I have to do is multiply to get moles. So if I take M times V, that's going to give me moles. That's a good equation for you. M times V, which is the same as C times V, if we use C for concentration instead. That's going to give me moles, which is going to get me almost to my mass. But mass, I also need to know my molar mass of HCl, which if I add 1.01 to 35.45, I get 36.46 grams per mole. So I can start out first. I know that moles of HCl is equal to my molarity times my volume, so 0.300 decimeters cubed times 6.00 moles decimeters to the -3. I have no idea what's going on next door. I apologize. Oh my goodness. Jeez Louise, maybe. This gives me 1.80 moles. But I don't want moles, I want mass. So I'm going to take that moles and multiply by the molar mass, 36.46 grams for every 1 mole. And I get 65.6 grams of HCl. We've got 4 minutes and one more big equation for us to learn to be able to finish up our review sheet, which is in the back if you get done with that and want to look at it at all. Are there questions, though, before our final problem? Okay. So, a little too far. So, hydrogen sulfide dissociates into hydrogen and it should be sulfate. Hydrogen sulfate dissociates into hydrogen and sulfate ions when in water. So the balanced reaction for that is H2SO4 goes to 2 H plus ions plus 1 SO4 to negative ion. Actually, we're not going to have time to go through this entire example. I'll go through that one more and post that one on YouTube. In the meantime, though, here's our big dilution equation. It's the number of moles of solute is equal to whatever our concentration times whatever our dilution is. So we said already that M1V1 is moles. Well, if I'm having the same stuff before and after, just more dilute than another, then I can make them equivalent of one another, and I'll just solve for an unknown. It's like we did with the gas laws with P1V1 is P2V2. We'll always have 3 knowns and 1 unknown. So, here's our first example. If we have 18 moles over liters of sulfuric acid, or if that's how much we want, or concentration that we want, how will we dilute it to form 25 centimeters cubed of 250 centimeters cubed of 3 mole per liter solution? So initially, I know my concentration, 18.0 moles over liters. I do not currently know the volume that I need of that to make the following solution, which is 250 centimeters cubed, which we're going to have to convert to liters because centimeters cubed is equal to milliliters. So we're going to have to convert that one. And then that would be multiplied by 3.0 moles over liters. So I would just rearrange this to solve for V after I've converted my volume of 250 centimeters cubed. I'm just going to leave it that way for now. Centimeters cubed times 3.0 moles over liters divided by 18.0 moles over liters. And that is all we have time for. So bless you. To finish that one again, all you need to do is convert